Alright, so hello again, good day. So welcome to another video. So this is a continuation of the module 4 Python user-defined data structure. Okay, so for this video, we'll discuss trees and graphs. So we'll start with trees first. So under the trees, we have two types of data. So we have the non-linear data structure, and then we have the hierarchical data structures. So we have here a quick overview of the tree. So this is the level 0 or the root, and we have the level 1, level 2, level 3, level 4, level 5, level 6, and so on and so forth if we have more nodes and more leaves below that. So every tree has a node called the root. So the very level 0, so there must be only one of that, so we call that one the root. And then each node can have one or more nodes as children. So as you guys can see right here, a node must always have a children. So it could be a leaf or it could be another node. Okay, so you cannot call that one a node if it doesn't have a children. So a node that has no children is called a leaf. So if that particular let's just say node for now doesn't have a children, we just call that one leaf instead of a node. So for example, this is a leaf since it doesn't have any children. This is another leaf because it doesn't have any children. So another leaf, 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 and then leaf. So those are the examples of leaves. Okay, so if it's node, then it must have at least one children. Okay, so here are the terminologies that are being used on the trees. So we have the edge. So this is an example of an edge. So in any tree, edge is a connecting link between two nodes. Okay, so this is a node and then this is another node. So the connection between that is called an edge. Okay, so this is another edge, 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 or just connecting lines or connecting wires. So we call that one edge. And then we also have a parent node. So I think it's very obvious. So that the reason why it's called a parent because it has a children. Okay, so you cannot call that one a parent if it doesn't have a children. So here are some examples of a parent node. So we have A, B, C, E, and G are parent nodes. So in any tree, the node which has child or children is called parent. And then a node which is predecessor of any other node is called the parent also. Okay, so the parent of E is B, the parent of B is A, the parent of D is B, the parent of F is B. Okay, so E and B and E and C and G are parents because they have children, unlike the D, I, J, F, K, and then H doesn't have the children. So that is why you cannot call this one as a parent anymore. Okay, so next one is a child. So I think this is also very obvious. So a child is a son or a daughter of a parent. So in this example, we have B and C are children of A. So probably they are, let's say, siblings. Okay, so this is their parent. So let's see, is a single mother or single father. And then we have here G and H are children of C. So G and H are also children of C. Okay, and then K is a child of G. Okay, if you want to add more, then D and E and F is a children of P. Okay, I and J is a children of E. Okay, so these are the descendant of any node is called as a child node. So we do also have siblings. So I think it's very obvious, just like what I mentioned a while ago. So B and C are siblings. D, E, and F are siblings. G and H are also siblings. I and J are also siblings. And then K doesn't have a sibling, so is one. And then A also doesn't have a sibling since he is a root. Okay, but of course, we do not know if it has a parent or not. But in this scenario, so he is a root. Okay, and then we also have ellipse, just like what I told you guys a while ago. So a leaf is a son or a daughter of a certain parent. Okay, so B and F is a leaf. Okay, and at the same time, you can call that one a leaf if it doesn't have children. Okay, so D, I, J, F K, and then H doesn't have children. So you can call that one a leaf. And then we also have a degree. So here, degree of B is 3, degree of 2, degree of A is 2, and then degree of F is 0. So how did that happen? So if you guys are going to take a look on this one, so the degree of B is 1, 2, and then 3. So the degree of A is 1 and 2. The degree of F is 0 since it doesn't have a connection below. So you could see that the degree is like the count of children that it has, okay, or the count of child that it has. So in any tree, degree is a node that is the total number of children it has. So if we have a degree, we also have a level. So I already mentioned this one a while ago. So this is level 0, the root, level 1, level 2, level 3, and so on and so forth. So we do also have a path. So I think this is also super obvious. So this is just a path from A to J. So this one is the connection that you can go to travel to J. So if we have here, let's see, a path between A and I. So this point right here will go to the left side. Okay, so that is the path from A to I. So if we have path from A to D, then it's just a straight line going to the left side. So A, B, and then D. So in this example, we have path A to J and then path C to K. Okay, so those are paths for the pink one and then for the green one. So we do also have a sub tree. So this itself is already a tree, but of course it has a sub tree. So this pink one right here, this B is a sub tree, the entirety, and then we have another sub tree right here. This is the letter E, which is another tree. So as you guys can see, as long as it has a children, a node, okay, left and right, or just one, that is already a subtree. Okay, same with this one. So it has a children, so that is already a subtree. And then we also have a height. So the height of a binary tree is the number of edges between the tree's root and its furthest lip. So the height of this one is 2 because that is the count of edges that it has from the top up to the bottom. So we have 1 and then 2. So the same with the others, of course. So 1, 2, 1, 2, 1, 2. So the height of this one is 2. And as you guys can see right here, we only have 1, 2, 1, 2, but the other one has 3. Okay, so 3 edges, 1, 2, 3. So that is why the height of this one is 3. So it depends on the highest count of the edges. So here are some application of tree structures. We have manipulate hierarchical data, make information easy to search, manipulate sorted lists of data, router algorithms, form of multi-stage decision making. So here are some example diagram. So we have here example of DOM, or this one is, forget the acronym, but it's object model. So anyway, yeah, that's it for the DOM. So we have the document, below that has the root element HTML, and we have the header, the head, the title, and then the body, and so on and so forth. Okay, so this is one example of a tree structure. So this is another kind of tree structure. Folders, it has subfolders, the topmost folder, okay, and then it has a tree subfolder. That subfolder has another folder inside of it, and so on and so forth. Okay, and then this is the most common diagram when it comes to trees. So this is the hierarchical data tree, or the tree view. Okay, so we also have here the types of tree structure. So we have binary structure, similar with binary search tree. We have the AVL tree, heap tree, half-moon tree, red black tree, split tree, and then tri tree or tree tree. Okay, so let's start with binary tree first. So I think it's also super obvious. Binary tree, that the reason why it's called binary, since it has two, or at most two children. Okay, so binary tree is a tree that data structure in which each node has at most two children, so which are referred to as the left child and the right child. So here are some properties of binary tree. So a tree with n nodes has exactly n minus 1 edges or branches. So you will see later on why it's always minus 1. So in a tree, every node except the root has exactly one parent, and the root node does not have a parent. Okay, that's the reason why it's called root. Okay, and there is exactly one path connecting any two nodes in a tree. And the maximum number of nodes in a binary tree of height k is 2 raised to k plus 1 minus 1, where k must be always greater or equal to 0. Okay, so we have here an example of a binary search tree. Okay, similar with this so-called binary tree. So the left subtree of a node contains nodes with lesser keys or equal keys than the node's key. The right subtree of a node contains nodes with greater keys than the node's key. The left and right subtree also needs to be a binary search tree. So with that, we can fulfill that this is really a binary tree. Okay, so at most two children, so the left side part, let's say this sub-tree, is always lower than the right side tree. So we can start with this one. This is lower than this one. This entire sub-tree of here is lower than the right side of the sub-tree right here. So if you're going to get another sub-tree of this one, so this is lower than this one. Okay, so that is how we implement a binary search tree. So if you're not going to follow that format, then we cannot apply binary search tree on that specific tree diagram or tree hierarchical data. Alright, so in here, a tree with n nodes has exactly n minus 1 edges. So as you guys can see, we have 1, 2, 3, 4. So we have 4 nodes. So 4 minus 1 is equal to the edges that we have. So 1, 2, 3. So we have 3 edges. Is it correct? So 4 nodes minus 1 is 3. So I think it's correct. So that is why a tree with n nodes has exactly n minus 1 edges or branches. Okay? And if you guys are going to take a look on this formula wherein k is the count of nodes. So in here, we have 15 nodes. So I do have here a Desma scientific calculator. So let us use, let me just close this one. Let us use this formula. So 2 raised to k plus 1 minus 1. So k here is the maximum number of nodes in a binary tree of height k. My apologies. K is the height. So in here, the height of this one is 1, 2, 3. Okay. So just go back in here just in case that you guys forget what is a height. So 2 raised to 3 minus, it doesn't want, minus 1. Okay, below that is minus 1. So 2 raised to k minus 1. Is it minus 1? Yeah, minus 1. So 2 raised to k plus 1. Okay, not minus. Okay, 2 raised to k, which is 3, and then plus 1 minus 1. So equal to 15. So if you guys are going to check this one, we do have a total of 15 nodes. Okay. So next one is the operations on binary search tree. So of course, we can insert a new node, we can delete an existing node, we can search an existing node, we can traverse the tree. So we do have two ways in doing that one. We have the depth first search, or the DFS. So we can do the pre-order, in order, and then the post order. So we also have the breadth first search, or the BFS. So we'll do that one step by step. So in insertion, so step 1, create a new node with given value and set its left and right to null. Step 2, check whether tree is empty. Step 3, if the tree is empty, then set root to new node. Step 4, if the tree is not empty, then check whether the value of is smaller or larger than the node. So here it is the root node, of course. And then step 5, if new node is smaller than or equal to the node, then move to its left child. If new node is larger than the node, then move to its right child. So again, going back from our structure a while ago, so the left side must be always smaller than the right side. So vice versa, the right side must be always larger than the left side. Okay. So repeat the above steps until we reach to the leaf node, and then once we reach that leaf node, after reaching the leaf node, insert the new node as left child if the new node is smaller or equal to that leaf node, or else insert it as a right child. Okay, so that is the way on how to insert a data using a binary search tree. Okay, so we also have deletion, of course. We have three cases for this one. So the first case is deleting a leaf node. So this is a node with no children. So this is the basic of basic. Step one, find the node to be deleted using search operation, and then delete that node. For the case two, so deleting a node with one child. So you have to find the node to be deleted using search operation. The same is step one. Step two, swap parent node and child node to make the node to be deleted becomes leaf. Third, delete the node using case one. So you always go back to the case one and to delete that specific node. For the last case, we have deleting a node with two children. So step one, find the node to be deleted using search operation. Swap the node to its in order successor. Repeat step two until the node becomes a leaf, and then delete the node using case one. So again, we went back to this case one to delete that specific node. Okay. So your goal in here in case 2 and case 3 is to make that just a leaf. Okay. So with that, once it is just a leaf, okay, then you can now apply case 1 to delete that specific node. Okay. And then we also have here search. So we have 6 steps for this one. So step 1, read the search element from the user. Step 2, compare the search element with the value of root node in the tree. Step 3, if both are matched, then display given node is found and terminate the function. If both are not matched, then check whether search element is smaller or larger than the node value. So if search element is smaller, then continue the search process in left subtree, because as we may all know, left subtree is always smaller than the right subtree. So if search element is larger, then we might want to search on the right side instead of the left side. So then continue the search process in right subtree. Okay, and then repeat the same until we find the exact element, or until the search element is compared with the leaf node. And then if we reach to the node having the value equal to the search value, then display element is found and terminate the function. If we reach the leaf node and if it is also not matched with the search element, then display element is not found and terminate the function. So of course, in searching, we have two possible results. So it's either element is found or element is not found. So either way, so we have to terminate the program. And then we also have here traverse. So this is a sample diagram. So we have here A, B, C, D, E, F, G. And then we also have here the numbers. So 1, 1, 2, 3, and then 2. So for the depth first search, or the DFS in order, so we have this one. So this is the order that you guys need to follow after applying this step 1 to 3. So we have D, B, E, A, F, C, G. So step 1 is recursively traverse the left subtree. Step 2, visit root node. And then step 3, recursively traverse the right subtree. So from left to root and then to the right. So that is the pattern for this one. So we have here D, B, E, A, C, my bad, A and then F. Okay, and then C and then G. Okay, so that is always the pattern. So D, B, E, A, F, C, and then G. Alright, so let us proceed to the next one. So we have here the pre-order, so the same. Okay, it's just that this one is a pre-order. So in here we have another or different format. So we have visit root node. So instead of starting from the very left subtree, so we'll start with the root. Okay, so and then step 2, recursively traverse the left subtree and then recursively traverse the right subtree. So in here we have A, B, D, E, C, F, and then G. Okay, so if you guys are confused, just follow these steps. Okay, so in order, we have left going to the root and then going to the right. For the pre-order, we have the root first and then going to the left and then going to the right. And then we have the post order. So this is still a depth first search or the DFS. So of course we'll start with the rightmost side. My bad. Leftmost side first and then rightmost side. And then we have here the node as the last one for the post order. So left side first, so D, E, B, and then right side F, G, C, and then the root, which is A. Okay, so that's it for the DFS or for the depth of first search. So we have the in order, pre-order, and then the post order. So for the breadth first traversal, so this one is by level order traversal. So we have 1, 2, 3, 4, and then 5. So here are the steps. So visit the root node, that is the 0 level. Visit next level from left to right. Okay, this is now the level 1. And then repeat step 2 until the last level and we're done or we finish. So in here, 1, 2, 3, 4, 5. I think this is a lot easier to follow since starting from level 0, just always go from left to right. Okay. So we have here an example for the in order, a pre-order, and then a post-order traversal. So we have here the root. Okay, so this is a binary search tree. So for the in order, we have the 4, 10, 12, 15, 18, 22, 24, 25, 31, 35, 44, 50, 66, 70, and then 90. Okay, so it's like from left to right. Okay, left side tree first, going to the root, and then the right subtree. So for the pre-order, we'll start with the root first, and then just apply the leftmost side order that we did a while ago. So 25, 15, 10, 4, 12, and then 22, 18, 24, and then going to the, I think it's 50, yeah, 50, 35, 31, 44, 70, 66, and then 90. So from the root first, going to the left side, left subtree, and then going to the root. It's like root of this subtree, this 50, and then applying the left subtree right here, going to the right. Okay, so that is a pattern for the pre-order. For the post-order, we start with the it's the left side. Yeah, it's the left subtree going to the right subtree and then the root. So in here we start with 4, 12, 10, and then followed by 18, 22, 24, and then 15, 31, 35, 44, and then 66, 70, 66, 90, 70, 50, and then 25. Okay, so even me sometimes we're confused, but just in case that you guys need to recall, just go back to this or just memorize this one. Okay, these steps right here. Oops, not this one, but this one. Okay, steps for the DFS. So we have an important note right here. So for duplicate values, there are no standard rule whether the tree can accept duplicate values nor where to place it. So left child or right child. So just in case it is allowed, since tree data structure is a user-defined structure, so programmer can decide how to handle this scenario. So you can let the user to input duplicate data, or it's either you can maybe warn the user already that this is a duplicate data, so you must change the inserted value or data. So that is completely up to you. So for the next topic, we do have here the graph. So a graph is a pictorial presentation of a set of objects where some pairs of objects are connected by links. Okay, so we have here the vertices. So A, C, B, D, and E are the vertices. And then I think it's the same with the edge. Okay, so the connecting wires or the connection between those two nodes. So before we call that one node, but in graph we call that one vertices now. Okay, so the connection between those two vertices is now, or still, the edge. So if the edge doesn't have an arrowhead, then it is a bidirectional. So since they don't have a head, okay, so they don't have an arrow, so they are bidirectional. So A will go to D, or D will go to A. So C will go to A will go to C. So vice versa. So we have an example right here. So this graph G can be defined as this one. So we will skip this part for now. So I would like you guys to take a look at this V. So vertices are A, B, C, and D, and A, B, C, and D, and E, right? So we have this one right here for the vertices. And then for the E, so we have the edge. So if we're talking about the edge, then we have to get the two nodes or the two vertices that is connecting or that is being connected to that edge. So we have BE, BD, BA, AC, AB, DC. Okay, so we have a total of how many? 1, 2, 3, 4, 5, 6, 7. So those are the possible connections since they are bidirectional or they are connected with each other. And then as you guys can see, so graph is equal to V, the vertices, and then E. So we just simply get this one and then paste it right here, this set right here, followed by a comma and then another set. Just copy this one and then paste it right there. So this is now our graph. Okay. So with that, we were able to define this one in a set. Okay, so these are their connections. And then graph data structure is represented using the following representations. So the first one is we have the adjacency matrix or vertices to vertices. So we have here, similar with the matrix. So I'm pretty sure you guys already done with this discrete math. So we have the A, B, C, and D and E, and then A, B, C, D, and E. So if there is a value on that specific column or row, then that only means that there is a connection. Okay, so just do take note that it's vertices to vertices, so we do have the same. So these are vertices and these are vertices. So in here we have A to C. So this one represent connection with from A to C. So that's the meaning of 1. So if it's a 0, A to A doesn't have a connection. Okay, so A to B has a connection, A to C has a connection, A to D has a connection, and so on and so forth. So as you guys can see right here, we have a loop. This connection will just go back to itself. So DD is right here. So that is why there is 1 right here, because it has a connection to itself. Okay, and then the rest doesn't have a connection with their own. Okay, except for D, of course. It has a connection to itself. So an example, node arrowhead defines the connection. Okay, so again, uh, this one doesn't have an arrowhead, so that only means that it's a bidirectional. Okay, I think this one is being applied to this next example. So in here we now have an arrowhead, so we have from A to B, B to A to C, D to D, D to E, and then B to E. So just find those possible connections. So B to E, we have here 1. Okay, so B to C is no connection, so that is why it's 0. So B to B doesn't have connection. B to A doesn't have a connection. So just find, an arrow where it is coming from, then where it is going to. So with that, you'll be able to identify the connection. So in here, B to A doesn't have connection. So B to A is a 0 since it's only A to B. Okay, so this one is the one that has a connection. And the other one, the other, from B to A doesn't have a connection at all. And we have another example here, or another form of matrix. We call that one incidence matrix. So a while ago, we have the vertices of vertices. So in here, we have vertices to edges. Okay, so we have labels already for the edges. So we have E1, E2 up to E8. Okay, so just find that one. So if it's 1, then okay, so we have here a meaning for the 1. So let's see, E6 is outgoing arrow from B, and then E7 is -1, is an incoming arrow. So if it's 1, it's outgoing, it's going to that specific vertices or vertice, or just a vertex. I think if it's single, I'm really sure. Just correct me, guys, to the comment section if I'm incorrect. Anyway, so we have here -1, so that is incoming. Okay, it is going to that specific vertices. Okay, so we have here A to B. Okay, so A to B has a connection of E1. Okay, so that's outgoing. And then we have here E2 is A to C, so that's also outgoing. And then as you guys can see right here, we have -1 for the A to D, or let's just say D to A rather. That's the most proper. But in here, so since we're reading A, so from D to A, so there is an incoming uh, arrow from D, so that is why it's -1. Okay, but in D to A, we're going to look for the D to A. Where is our D to A? Where is this one? E3. This is E3, right? E3. E3. Okay. So D to A is E3. So it's just 1. Okay. So just do take note on the arrows. If it's incoming, then that's -1. If it's outgoing, then that is positive. Okay. So just recheck everything with this one. So I will not be reading or verifying everything anymore, since it would take us longer. Anyway, that's it for the incidence matrix. So that is vertices to edges. We also have here adjacency array. So in here we have A, and then so I think it would be better if you guys would take a look on this one first. So these are your reference array, starting from 0 up to 4, or let's say up to how many vertices we have in here. So A, B, C, D, and then E. So there is reason why this letter E was crossed out. Okay, so let's start with letter A. So as you guys can see, it is going to B, C, right? It has an arrow going to B and C, because A is really going to B, or it is also going to C. So that is why we have B, C right here for the array 0, or the letter A. For the letter B, we have an outgoing, going to E and then going to D. That is why we have here D and then E. For letter C, we have 1 only, so that is D. For the letter D, we have D to A, and then D to E, and then D to D. Okay, so A, D, and then E. So these are adjacency array. And then the reason why the letter E was crossed out, because it doesn't have arrow going to the other vertices. So it's keep on, incoming, not outgoing. So with that, we can just simply cross this one out. So this one doesn't met the adjacency format. Is reference array contains all verticals, and each element has connected to adjacency array. So adjacency array contains all outgoing direction from a vertex. Okay. So the next one is a graph traversal. So this is a technique to access elements in a graphs or in a graph. So we have DFS, so depth first search. So we have step 1 to step 7 right here. So define a stack of size total number of vertices in a graph. Step 2, select any vertex as a starting point for traversal. Visit that vertex and push it onto the stack. And then step 3, visit any one of the adjacent vertices of the vertex which is at top of the stack which is not visited, and push it onto the stack. Step 4, repeat step 3 until there are no new vertex to be visited from the vertex on top of the stack. And then when there is no new vertex to be visited, then use backtracking and pop one vertex from the stack. Step 6, repeat step 3, 4, and then 5 until stack becomes empty. And then step 7, when stack becomes empty, then produce final spanning tree by removing unused edges from the graph. So I know this one is quite hard to follow if we don't have an example. So that is why we'll go straight to the example. So we have here the graph. So consider the following example graph to perform DFS traversal. So I hope you guys can read this one. Let me just make this one bigger. Okay, so step 1, select the vertex A as a starting point. So visit A. So just put a green marker in there, or a background color. So that only means that we already visited that vertex. So you can visit any starting point, since it says here visit that vertex, and or select any, rather it's right here, select any vertex as your starting point. So in here I think it's, we normally go to the letter A, so we'll just start with letter A and then just put it right here as our first step. Excuse me. And then step 2, visit any adjacent vertex of A which is not yet visited. So let's just say for now B, so we can actually visit E or D, but in this example let's just choose B. So push newly visited vertex B onto the stack. So we now have the B right here. Okay, so just apply the whatever you guys have learned in stack. So we have to put that one at the very top, okay, not at the bottom. Okay. And then step 3, visit any adjacent vertex of B which is not visited. So let's say C. Okay, so push C onto the stack. So we now have A, B, C. Step 4. Okay, so let me just move my mic. So visit any adjacent vertex of C which is not visited. So do we have a... There you go. So let me just make this one smaller. Alright. So visit an adjacent vertex of C which is not visited. So in this case, let's just say E, and then push E onto the stack. So we have A, B, C, and E. And then visit an adjacent vertex of E which is not visited. Let's say D. So we can actually go to F, but let's just say D for now. And then push D onto the stack. So we now have the D right here. So in here, as you guys can see, there is no new vertex to be visited, since A, B, and then E, or this is A and E actually, are already visited. So use backtrack, pop D from the stack, and then, so we already used the backtrack, so we went back to E, and then we popped that one, or we deleted the D, so we went back to letter E. So step 7, visit an adjacent vertex of E which is not visited. So in this case, we'll go to F. Okay, so push F onto the stack. So instead of D, we'll go to the right side, okay, which is the F. So A, B, C, E, and then F. Step number 8, so visit an adjacent vertex of F which is not visited. So let's see, of course we don't have a choice, C and E were already visited, so we will visit the letter G. Okay, so push G onto the stack. Step 9, so in here there is no new vertex to be visited from G, so use backtrack. Okay, so we'll remove G, pop that one out, and then we'll go to F. And then the same, so there is no new vertex to be visited from F, so just pop that F right here, and then we'll go back to letter E, and the same, so there is no new vertex to be visited from E, so use backtrack. So pop that one out, that letter E, and then go back to letter C. And then again the same, there is no new vertex since we already visited everything, so pop that one out, and then go back to B. So again, there is no new vertex to be visited, so pop that one out, go back to A. And then there is no new vertex that we can visit, since I think again every vertex has already visited, so remove that A. And then stack became empty, so we are now on this step 7. So finally, so going back here, so stop DFS traversal, and then the final result of DFS traversal is following spanning tree. Okay, from A, B to C, E, D, F, and then G, and then it, you know, it uh, it went back, or it backtracked until it became empty. So with that, we were able to form this spanning tree, okay, or this formation of tree. So we have here another example. So instead of stop, okay, so we now or we have here a queue. Okay, so define a queue of size total number of vertices in graph. Select any vertex as a starting point for traversal. Visit that vertex and insert it into the queue. Visit all the adjacent vertices of the vertex which is at front of the queue, which is not visited, and insert them into the queue. When there is no new vertex to be visited from the vertex at front of the queue, then delete that vertex from the queue. Step 5. Repeat step 3 and 4 until queue becomes empty. When queue becomes empty, then produce final spanning tree by removing and use edges from the graph. So this is actually quite similar with the stack. Let's see. Okay, so we have the same example. So select the vertex A as a starting point, so visit A. So insert A into the queue. So instead of this formation from bottom to top, we have here from left to right. Okay. Step 2, visit all adjacent vertices of A which are not visited. So this one we're going to visit at one time. So instead of B to E and then going to D. So here we'll just put everything that is adjacent to A. So we have D, E, and then B. Okay, so just insert them right here, D, E, and B. So insert newly visited vertices into the queue and delete A from the queue. It's very important. So after visiting the adjacent vertices, you guys have to delete the last one. The where we have based that adjacent datas, okay, or vertices. Step 3, visit all adjacent vertices of D. Okay, so we can base it right here. So we will start with the D, okay, before E and then before B. So D first. Visit all adjacent vertices of D which are not visited. So there is no vertex, so just delete the D. Okay, since the A and E were already visited. So we are now at E. So visit all the adjacent vertices of E right here. So we do have C and F. Okay, we cannot put B here anymore since it's already on the last step right here. So we can input C and then F, or we can visit rather C and then F. So just put here C and then F. Step 5, visit all adjacent vertices of B which are not visited. So there is no vertex, so just simply delete that B. So this is step 5. Now we repeat it in here. So step 6, visit all adjacent vertices of C which are not visited. So C. So as you guys can see, we don't have a choice, but choose G since that is the only vertices that is not yet visited. So just put here G. So our last basis was F. So visit all adjacent vertices of F that were not visited. So again, there is no vertices since everything were already visited. So just delete that one. And then the same with G. So visit everything that is not yet visited. But since there is no existing vertex that is not visited, then just delete that one. Okay. So we have here an empty queue. So step the BFS process. Final result of BFS is a spanning tree as shown below. Okay, so we have here the first one, A, B, and D, and then E is going to C and F, and then from C going to G. Alright, so that's pretty much it for the trees and graph. So if you guys have a question or clarification, so just let me know. Just comment to the comment section below. So yeah, thank you guys for watching and see you guys the next video. So goodbye and peace.